Hello everyone, this is Byungmin Kim from Triple IXR Lab. Today I'll be presenting SmartBench, a recent benchmark paper which asks a simple but important question. How well can current LLMs actually detect anomalies inside a smart home? Most existing LLM-based smart home work, including Simu Home, which we looked at recently, focuses on understanding and executing user commands. The assistant receives an instruction and figures out the right sequence of device actions. But the authors of SmartBench argue that this misses a core capability. A real smart home assistant shouldn't only respond to commands, it should also perceive on its own when the home itself is in an anomalous state, and it should be able to explain why and suggest what to do. That perception side is what prior benchmarks have largely overlooked, and it's exactly what SmartBench targets. SmartBench makes three main contributions. First, it shifts the evaluation framing from execution to perception. The model detects anomalies from observation alone, without any user command telling it to look. Second, it introduces a 15-category anomaly taxonomy, with every anomalous sample paired one-to-one with a normal counterpart built via four controlled edit operations. And third, it defines a three-tier capability hierarchy that measures not just whether the model detects an anomaly, but whether it can localize the responsible device and explain the underlying cause. The benchmark splits into two tasks. Context independent gives the model a single point snapshot, all device states and environmental parameters at one moment. Anomalies here are detectable from a single frame. For example, the living room air conditioner is in cooling mode while the heater is in heating mode at the same time. One snapshot is enough to see the conflict. On the other hand, context dependent gives a temporal sequence of state transitions as timestamp, device, state, location tuples. Here the model has to reason causally and temporally across the whole window. For example, the humidifier has been turned on, but after an hour the humidity is actually dropping instead of rising, suggesting the humidifier is malfunctioning. No single timestamp looks wrong. You have to watch the sequence to see it. The dataset is built with a three-stage synthetic pipeline. In stage 1, normal samples are generated from a real IoT dataset and from virtual smart home scenarios using GPT-5, with long sequences compressed to preserve semantics. In stage 2, GPT-5 Mini auto-checks every sample for device transition validity, temporal consistency, and semantic consistency. And in stage 3, anomalies are injected by applying four controlled edit operations: insertion, deletion, temporal shift, and value adjustment, producing one-to-one paired normal and anomalous samples. SmartBench proposes a three-tier hierarchy of increasing difficulty. Tier 1 is detect. Is something wrong in the home right now? Measured by F1 and false positive rate. Tier 2 is localize. Which device is responsible? Measured by the AL score, the Jaccard overlap between predicted and ground truth evidence device sets. Tier 3 is explain. Why is it wrong and what should be done? Measured by the AC score, a 1 to 5 rating from GPT-5 Mini, judging how well the model's rationale matches the human annotated explanation. The point of this hierarchy is that only a model clearing all three tiers can actually help a user fix a problem. Here are the main results across 10 representative LLMs. Gemini 3 was the best, which is 79.3% F1 on snapshots, but on sequences the best is only 67%, and that came with a false positive rate of 78%, meaning it flags almost everything as anomalous. So this is far from deployable. And context-dependent texts are consistently harder than context-independent ones. The authors attribute this to the lost in the middle effect, where long sequences cause models to miss key signals. Second, detection does not imply understanding. Even when models correctly flag an anomaly, they often fail to localize the responsible device or explain the cause. The authors also found that scaling alone does not solve it. Moving from Llama 8 billion to 405 billion improved only 9 percent point, so parameter count cannot substitute for the reasoning this task demands. Context compression and in-context learning offer only partial relief. They close part of the gap but leave current LLMs well short of real-world deployment. To conclude, SmartBench is the first benchmark that evaluates LLMs on smart home anomaly perception, with various samples and 15 categories and ground truth rationals, giving the community to a concrete yardstick for capability prior work overlooked. But I see three limitations worth flagging. First, there's a circularity issue. No more samples are generated by GPT-5, compliance checked by GPT-5 Mini, and rational quality is also judged by GPT-5 Mini. This risks favoring models from the same family as a data generator. Second, the anomaly semantics are author-defined and not validated against what real users would perceive as anomalous. User intent and personalized exceptions are not accounted for. And third, the AC score relies on a single LLM judge with no human inter-annotator agreement and no multi-judge ensemble, making fine-grained differences difficult to interpret. This is the end of my presentation. Thank you for listening.